Hello everyone and welcome to the lecture on Amazon Elastic Kubernetes Service EKS. So in this lecture I will be covering all these topics. What is Amazon EKS, common use cases, EKS architecture, EKS deployment options, setting up your environment for Amazon EKS clusters, key components, EKS node types, and within that node types there will be three different types of node: managed node groups, self-managed, and AWS Fargate. Then I will be covering one of the storage driver, which is Amazon EBS CSI driver, VPC and subnet requirements, and finally logging and monitoring on Amazon EKS. So what is the Amazon EKS? First, managed Kubernetes service. Amazon Elastic Kubernetes Service EKS is a fully managed service that makes it easy to run Kubernetes on AWS without needing to install, operate, and maintain your own Kubernetes control plane or nodes. Second, automates provisioning, scaling, and management. So EKS automates key tasks such as provisioning, patching, node scaling, and updates, simplifying the management of Kubernetes clusters. Third, Amazon EKS provides a secure, reliable platform for running Kubernetes workloads with multiple layers of security and compliance certifications. Fourth, EKS runs on the AWS global infrastructure, benefiting from high availability, security, and performance across multiple regions and availability zones. Fifth, Amazon EKS seamlessly integrates with other AWS services such as Amazon ECR for container images, IAM for access control, and CloudWatch for monitoring. Sixth, with EKS, users can easily deploy and scale containerized applications using Kubernetes without the complexity of managing the underlying infrastructure. Seventh, Amazon EKS follows a pay-as-you-go pricing model, where users only pay for the EC2 instances and other resources consumed by their Kubernetes applications with no additional charges for EKS management. So this is the high level overview of Amazon EKS. So we have Amazon EKS cluster, which is powered by something called as Amazon EKS distribution. Then it can be run on AWS Fargate, which is a serverless option, or you can choose Amazon EC2, where it will deploy on Amazon EC2 worker nodes, and then finally you run Kubernetes apps. Doesn't matter which option you choose. And then you have Amazon EKS dashboard in AWS console. So through the EKS dashboard, you can view and explore running Kubernetes apps. One more option we have is Amazon EKS on Outpost. Outpost is basically you have your own on-premises data center and you install Amazon EKS on Outpost. So it's basically an extension of AWS Cloud onto your on-premises. So basically you install AWS Cloud locally, in the sense not the whole thing, but few services, and that includes Amazon EKS as well. So you can create Kubernetes cluster on Outpost, which is again powered by EKS distros, and you have two options, like local clusters, which is completely on Outpost, which is on local data center, or you can have extended, which is a mixture of AWS Cloud plus Outpost. And then finally you have the same, you run apps and you have the EKS dashboard in the AWS console. And last option is Amazon EKS Anywhere, which is manage EKS distro Kubernetes cluster. So basically it's a distro which you can download and install, and you have self-managed resources, so your own premises infrastructure. So you have to completely manage by yourself. You run Kubernetes apps as usual, and you can still watch, or you can still monitor that through Amazon EKS dashboard in the AWS Cloud console. Okay, common use cases in Amazon EKS. 1. Use elastic load balancing to ensure applications are highly available across multiple availability zones. Second, utilize Kubernetes service discovery feature with AWS Cloud Map or Amazon VPC Lattice to build resilient systems. Third, manage continuous integration and continuous deployment CI/CD pipelines for automated building, testing, and deployment of applications. Fourth, serverless applications. So you run serverless applications using AWS Fargate with Amazon EKS, focusing solely on application development. Then you have machine learning workloads compatible with popular machine learning frameworks like TensorFlow, MXNet, and PyTorch, with GPU support for complex tasks. Sixth, use Amazon EKS Anywhere to operate Kubernetes clusters on your own infrastructure, consistent with Amazon EKS in the cloud. Utilize Spot instances to run batch processing and big data workloads like Apache Hadoop and Spark at a fraction of the cost. Integrate with AWS security services like IAM, Identity and Access Management, Amazon VPC, and AWS Key Management Service KMS to ensure data privacy, protection, and industry compliance. Okay, next is Amazon EKS architecture overview. So Amazon EKS ensures each cluster has its own separate control plane, preventing overlaps between clusters or AWS accounts, and this design keeps each cluster's infrastructure isolated. So you have a separate control plane per cluster. And second, the control plane is distributed across at least 2 API server instances and 3 etcd etcd instances in 3 AWS availability zones within a region, enhancing resilience. Amazon EKS actively monitors control plane instances and makes necessary adjustment to maintain optimal performance, ensuring smooth operation. Fourth, if a control plane instance fails, Amazon EKS promptly replaces it using a different availability zone if needed, minimizing disruptions. Fifth, Amazon EKS uses Amazon VPC to restrict traffic between control plane components within a cluster, preventing unauthorized communication from other clusters or AWS accounts. Sixth, AWS Fargate, Carpenter, managed node groups, self-managed nodes. So these are the compute options available. So Amazon EKS offers all these various compute options, which I just talked about. Fargate, that includes serverless Fargate and high performance Carpenter autoscaler. Then you have managed node groups with automation and customization, and self-managed nodes for full control. The choice of node type depends on user preferences, whether prioritizing simplicity, Fargate for example, or efficiency, Carpenter. A blend of automation and customization, which is for when we use managed node groups, or complete control when we use self-managed nodes. So I'll be covering these in next few slides. Okay, Amazon EKS deployment options. First, we have run Kubernetes in the cloud, AWS cloud, without the need to install, operate, or maintain your own Kubernetes cluster control plane or nodes. So this option provides a fully managed Kubernetes experience, allowing you to focus on your application. So this is the default option. So if you just go to AWS cloud and launch Amazon EKS, this is the default option. Then as I talked about, you have Amazon AWS Outpost, which enables native AWS services, infrastructure, and operating models in your on-premises facilities. With Amazon EKS on Outpost, you have two options. First one, extended clusters. The Kubernetes control plane runs in an AWS region while the nodes run on Outpost, providing a hybrid deployment model. Then you have local clusters also. So the entire Kubernetes cluster, including both the control plane and nodes, run locally on Outpost for a fully on-premises deployment. And finally, Amazon EKS Anywhere. So this deployment option allows you to easily create and operate Kubernetes clusters on premises. Amazon EKS Anywhere is built on the same Amazon EKS distro used by Amazon EKS in the cloud, ensuring consistency across environments and enabling a hybrid cloud strategy. Amazon EKS distro. Amazon EKS distro is an open source distribution of the same Kubernetes software and dependencies deployed by Amazon EKS in the cloud. It follows the same Kubernetes version release cycle as Amazon EKS, providing a consistent foundation for Kubernetes deployment across cloud or on-premises environments. Setting up your environment for Amazon EKS. So first is you create an access key, sign into AWS console, you create an access key and secret key and access key, download the access key ID and secret key onto your local machine. Then you configure the credentials, region and output format. So you just set up the AWS CLI using those access key. Second, you obtain and verify your security credentials. So after you just run the commands, like for example AWS get caller identity and all those things. Run STS get caller identity to verify AWS credentials for your IAM user. So make sure it is set up properly. Then third, you install essential tools for resource management. So you have to install EKS CTL so install EKS CTL so that you can from CLI you can manage the whole EKS cluster. So it's basically EKS CTL control, same like kubectl, and in an infrastructure as code IAC utility that uses AWS CloudFormation to easily create Amazon EKS clusters and additional Kubernetes resources. So EKS CTL uses CloudFormation to create your clusters. Then you have Terraform for advanced users. For those accustomed to automating AWS infrastructure provisioning and deployment, install Terraform. And you can install kubectl then after that. So basically to interact with your Kubernetes cluster or the EKS cluster. Kubectl is again an open source command line tool. And then you set up the local development environment. So you can set up Minikube or Kind. If you are new to Kubernetes, consider installing a local deployment tool like Minikube or Kind. These tools allow you to manage an EKS cluster on your local machine for development and testing purposes. And then you can install Helm for package installation and management. So this one, Minikube or Kind, is like if you want to play around before you start directly interacting with the Kubernetes EKS cluster. Then you have Helm for all package management or package installation and management, which is basically a popular package manager for Kubernetes that helps you like package your applications in something called as Helm charts. Okay, so Amazon EKS clusters key components. The control plane is the brain of your Amazon EKS clusters, consisting of nodes that run essential Kubernetes software such as etcd for distributed key value storage and Kubernetes API server. Each cluster has its own dedicated single tenant control plane, ensuring isolation and security. The control plane is hosted in an AWS managed account, so relieving you of the burden of managing the underlying infrastructure. Then we have EKS nodes. Nodes are the worker machines in your clusters responsible for running your containerized applications. These are Amazon EC2 instances that connect to clusters control plane via the API server endpoint. Unlike the control plane, nodes are managed in your own AWS account, giving you full control over the compute resources and allowing you to customize them according to your workload requirements. Security and resilience are top priorities in Amazon EKS cluster. All data stored by etcd nodes and their associated Amazon EBS volumes is encrypted using AWS Key Management Service KMS keys, ensuring the confidentiality and integrity of your cluster's control plane data. The control plane is provisioned across multiple availability zones (AZs) to guarantee high availability and fault tolerance. Additionally, an elastic load balancer, network load balancer, sits in front of the control plane, efficiently distributing traffic and enhancing the cluster's overall resilience and performance. To enable smooth communication between the control plane and nodes, Amazon EKS provides elastic network interfaces in your VPC subnets. These interfaces act as a bridge, facilitating connectivity from the control plane instances to the nodes, and this connectivity is crucial for supporting essential Kubernetes operations like kubectl exec for executing commands in containers, accessing container logs, and enabling proxy data flows. So with this connectivity in place, you can efficiently manage and monitor your containerized application. Okay, Amazon EKS node types. So we'll see that there are actually three node types. One is managed node groups, second is self-managed nodes, and third one is AWS Fargate. So first one, EKS managed node groups. Amazon EKS takes care of, so this is the default option, default cluster option. So Amazon EKS takes care of creating and managing the Amazon EC2 instances for your worker nodes, provisioning them within an auto-scaling group. This simplifies the process of setting up and maintaining your Kubernetes cluster. Second, when creating a managed node group, you specify the subnets in which auto-scaling group should deploy instances, and this allows you to distribute your nodes across multiple availability zones, enhancing the resilience and availability. Managed node groups resources, including EC2 instances and auto-scaling groups, are automatically tagged by Amazon EKS. So this ensures they are properly configured to work with Kubernetes cluster autoscaler. You can use custom launch templates when creating managed node groups, giving you greater control over the configuration of your worker nodes. This includes the ability to specify extra kubelet arguments, use custom AMIs, and more. So tailoring your nodes to your specific requirements. When running stateful applications that use ABS volumes and Kubernetes autoscaling, it is recommended to configure multiple node groups, each scoped to single availability zone. This ensures proper distribution and management of stateful workloads across your cluster. Amazon EKS follows a shared responsibility model for managing vulnerabilities and security patches. For managed node groups, use Amazon EKS optimized AMIs. Amazon EKS is responsible for building patched version, while you are responsible for deploying them. With custom AMIs, you handle both building and deploying the patched versions. Managed node groups can be launched in both public and private subnets. For public subnets, ensure that map public IP on launch. So there is a parameter called map public IP on launch is set to true. For private subnets, nodes need access to Amazon ECR and other necessary service via NAT gateways or AWS private link VPC endpoints. You can create multiple managed node groups within a single Amazon EKS cluster, each with different configurations or AMIs. This allows you to cater to diverse workload requirements such as running standard Linux workloads and GPU accelerated workloads simultaneously. If a managed node group encounters an Amazon EC2 instance status check failure, Amazon EKS provides error codes to help diagnose the issue. This enables troubleshooting and resolution. Amazon EKS automatically adds Kubernetes labels to managed node groups instances prefixed with eks.amazonaws.com. Additionally, nodes are automatically drained using Kubernetes API during termination or updates, ensuring graceful pod termination and rescheduling. Pod disruption budgets, known as PDBs, are respected during updates. So there is an object within Kubernetes which is known as pod disruption budgets, PDBs, and they are respected during updates. There are no additional costs for using Amazon EKS managed node groups. You only pay for the AWS resources you provision, such as EC2 instances and EBS volumes, making it a cost-effective solution for managing your Kubernetes worker nodes. To encrypt Amazon EBS volumes for your nodes, you can deploy the nodes using a launch template or enable encryption by default for all new EBS volumes in your account. This ensures the security and confidentiality of your data at rest. Now we see self-managed nodes. So self-managed nodes in an Amazon EKS cluster are Amazon EC2 instances that run in your own AWS account, giving you full control over their configuration and management. As these nodes are essentially EC2 instances, you are billed based on the standard Amazon EC2 pricing model. Self-managed nodes connect to the control plane of your Amazon EKS cluster through the cluster API server endpoint. This enables seamless communication between the nodes and the control plane, facilitating the scheduling and execution of pods on the nodes. Ensuring proper connectivity is crucial for smooth operation. An Amazon EKS cluster can contain several node groups, each consisting of one or more nodes deployed in an Amazon EC2 auto-scaling group. The instance types within a node group can vary, allowing you to leverage attribute-based instance type selection with tools like Carpenter for optimal resource utilization. This flexibility enables you to tailor your node configuration to specific workload requirements. Amazon EKS provides specialized Amazon Machine Images AMIs called Amazon EKS Optimized AMIs. These AMIs are pre-configured to work seamlessly with Amazon EKS, containing essential components such as Containerd, kubelet, and the AWS IAM Authenticator. They also include a specialized bootstrap script that automatically discovers and connects the node to your cluster's control plane, simplifying the setup process. If you restrict access to the public endpoint of your cluster using CIDR blocks, it is recommended to enable private endpoint access. This ensures that nodes can communicate with cluster securely. Without the private endpoint enabled, the CIDR blocks specified for public access must include the egress sources from your VPC to allow proper communication between the nodes and the cluster control plane. All self-managed nodes in an Amazon EKS cluster must be associated with Amazon EKS node IAM role, and this role is essential for the nodes to integrate with AWS Identity and Access Management IAM for authentication and authorization processes within the cluster. Ensuring the correct IAM role is attached to the nodes is also crucial for maintaining the security and integrity of your cluster. When adding self-managed nodes to your Amazon EKS cluster manually, it is important to add a specific tag to each node. This tag helps identify and manage the nodes as part of your cluster. If you follow the guide for adding self-managed nodes, the required tag is automatically added to the nodes for you, which will streamline the whole process. And proper tagging is essential for effective node management and cluster operations. So basically, you spin up your own EC2 instances and you make that part of the EKS cluster through proper tagging, the required tag, so that they become part of the EKS cluster. If you don't choose this second option, the first option, which is the managed node groups, the default one, so that will launch EC2 instances with all the required software, everything by itself. But in this case, you have to do some like install some software and all. If you start, for example, this particular option 4th, right? So you may build up the AMI by yourself, custom AMI, or you can install all the containerd, Docker, or all these tools, kubelet by yourself, or you can use the EKS optimized AMIs and then customize it, or you can use it as it is. But in case of first option, you just specify how many nodes you want, and the cluster setup process will launch that many number of nodes automatically for you. But in this, you have to manually join these nodes as part of the EKS cluster. Okay, last option is AWS Fargate. AWS Fargate provides on-demand right-sized compute capacity for containers, allowing you to run Kubernetes pods without the need to provision, configure, or manage the underlying servers or clusters. This serverless approach simplifies container deployment and scaling. So basically, this is like a Lambda, like a serverless compute, but not like exactly Lambda technology, but you will not see any servers. So it will be completely hidden from you, and you just specify this particular technology, and containers will come and go, or it can be long running container, pods, deployment, whatever, but you will never see the backend. Fargate, there's something called as Fargate profiles. So Fargate profiles, defined as part of your Amazon EKS cluster, allow you to control which pods start on Fargate and how they run. These profiles use controllers built by AWS to schedule pods onto Fargate, providing granular control over pod execution. AWS Fargate integrates with Amazon EKS using built-in controllers that run as part of the managed Kubernetes control plane. These controllers, including a new scheduler and admission controllers, work alongside the default Kubernetes cluster scheduler. Work alongside the default Kubernetes scheduler to seamlessly schedule pods onto Fargate. Each pod running on Fargate has its own isolation boundary, preventing access to host-based resources used by other pods. This VM-level isolation enhances security and adds defense in depth for Kubernetes application, mitigating the impact of container escapes. Fargate supports network load balancers and application load balancers using IP targets. However, Fargate exposed services only run on target type IP mode, not on node IP mode. Connect via service name for communication between services running on managed nodes and Fargate. Some considerations: no daemon sets, privileged containers, or host port / host network. So Fargate has some limitation such as not supporting daemon sets, privileged containers, or use of host port or host network in the pod manifest. Reconfigure daemons to run as sidecar containers if needed, and be aware of these constraints when designing your application architecture. Reason is daemon sets run on a per node basis, but in this case we don't see or operate on node level because it's serverless compute. So that's why daemon sets are not supported. Similar concept holds for privileged containers and host port and host network. To deploy pods on Fargate, ensure your VPC has private subnets available, as Fargate's pods are only supported on private subnets. Enable DNS resolution and DNS hostname for your VPC, and consider using VPC secondary CIDR blocks to increase the number of available IP addresses for pods. Utilize the vertical pod autoscaler to set the initial CPU and memory for your Fargate pods, and then use the horizontal pod autoscaler to scale the number of pods based on demand. Set the vertical pod autoscaler mode to auto or recreate for automatic redeployment with larger resource combination. So it's not available. AWS Fargate is not currently available for deployment in AWS Outpost, AWS Wavelength, or AWS local zones. 10th, Amazon EKS periodically patches Fargate pods to maintain security. While efforts are made to minimize impact, some pods may be deleted if they are not successfully evicted. So implement strategies to minimize disruption during patching, such as using pod disruption budgets and redundancy. Okay, Fargate pods can automatically mount on Amazon EFS file system, providing a scalable and shared storage solution. However, dynamic provisioning of Amazon EBS volumes is not supported for Fargate pods. Use static provisioning or consider alternative storage option. To automatically clean up pods related to completed or failed Kubernetes jobs, specify a time to live (TTL) period using the TTL controller in your job manifest, and this helps optimize resource utilization and manage cost by promptly removing pods that are no longer needed. Okay, next is we'll just talk about one storage option, which is the most commonly used EBS, Amazon EBS CSI driver. So the Amazon EBS CSI driver adheres to the industry standard container storage interface CSI specification, ensuring compatibility and interoperability with Kubernetes and other container orchestration platforms. And this seamless integration allows users to easily attach, mount, and manage EBS volumes for stateful applications on Kubernetes. So when we are talking about stateful applications or stateful databases, if you want to run, for example, something like Cassandra or something, then EBS volumes will come into pictures. With the Amazon EBS CSI driver, you can dynamically provision and manage EBS volumes for your containerized applications. This simplifies the process of providing reliable and persistent storage to your pods, automating volume creation and attachment as part of the pod lifecycle. EBS CSI driver offers a range of advanced storage management features, including volume resizing, snapshotting, and cloning. These capabilities enhance data management and protection within Kubernetes environments. Additionally, the driver supports encryption for data at rest, ensuring your volume data is secure and compliant with organizational policies. By leveraging the Amazon EBS CSI driver, you can build and deploy stateful application in Kubernetes with enhanced storage flexibility and scalability. So the driver enables you to dynamically adjust storage capacity and performance based on your application requirements. The Amazon EBS CSI driver seamlessly integrates with Kubernetes built-in security features such as role-based access control and network policies. With Amazon EBS CSI driver, you can optimize your storage utilization and cost efficiently by dynamically provisioning and managing EBS volumes based on your application storage requirements. So this helps reduce storage waste and over provisioning, allowing you to pay only for the storage you actually need and scale up or down as your demand change. The EBS CSI driver provides flexibility and customization options such as the ability to use custom Amazon machine images AMIs with pre-installed EBS CSI drivers. This allows you to have greater control over your runtime environment and customize it as per your needs. The Amazon EBS CSI driver takes advantage of EBS performance features such as provisioned IOPS, input-output operations per second provisioned IOPS, to meet the demands of high-performance application. And by leveraging these capabilities, you can ensure that your stateful applications have the necessary storage performance and scalability to handle intense workloads and peak traffic. Okay, next is some VPC and subnet requirements for Amazon EKS clusters. First, ensure your VPC has enough available IP addresses for the cluster, nodes and Kubernetes clusters and Kubernetes resources. If the VPC lacks sufficient IP addresses, update the cluster configuration to change the subnets and security groups used by the cluster. When changing subnets after cluster creation, all new subnets must be in the same set of availability zones as originally provided during cluster creation. If you need more IP addresses, associate additional private or public CIDR blocks with your VPC either before or after creating your cluster. To conserve IP addresses, consider using a transit gateway with a shared services VPC. The VPC must have DNS hostname and DNS resolution support enabled for nodes to register with your cluster. When creating a cluster, Amazon EKS creates elastic network interfaces in the specified subnets to enable communication between your cluster and VPC and to facilitate Kubernetes features like kubectl exec and log. The subnets you specify when creating or updating a cluster must have at least 6 IP addresses available for use by Amazon EKS, with 16 or more recommended for optimal performance and scalability. Note that the subnets for your cluster cannot reside in AWS Outpost, Wavelength or local zones. You can deploy nodes and Kubernetes resources to the same subnets specified during cluster creation or to different subnets. Ensure that any subnet you deploy to has enough available IP addresses. It is recommended to use private subnets for nodes when possible and public subnets for load balancers. If deploying nodes to a public subnet, ensure that the subnet is configured to auto-assign IPv4 addresses or IPv6 addresses, IPv4 public addresses or IPv6 addresses. For IPv6 support, associate an IPv6 CIDR block with your VPC. If deploying nodes to a private subnet without a route to a NAT device, IPv4 or egress-only gateway IPv6, add VPC endpoints using AWS private link for all the AWS services. For all the AWS services your nodes and pods need to communicate with. Okay, logging and monitoring options within Amazon EKS. So we have first we'll see the logging options. So we have Amazon CloudWatch Container Insights, and this collects logs. It collects, aggregates and summarizes metrics and logs from your containerized applications and microservices. Then we have AWS CloudTrail, which is used for logging API calls by user, role or service, and this is for control plane only. Then we have AWS Fargate Log, which streams logs to AWS services or partner router tools. This one uses AWS for something called as Fluent Bit, and logs can be streamed to other AWS services or partner tools. And this is only for AWS Fargate instances. Then we have coming to monitoring options. To monitor your cluster, we have first is CloudWatch Container Insights. CloudWatch Container Insight again collects, aggregates and summarizes metrics and logs from your containerized applications and microservices. Then we have AWS Distro for open telemetry, ADOT. It collects and sends correlated metrics, trace data and metadata to AWS monitoring services or partners. It can be set up through CloudWatch Container Insights. Then we have Amazon DevOps group. It detects node level operational performance and availability. Then we have AWS X-Ray. It receives trace data about your application. This trace data includes incoming and outgoing request and metadata about the request. For Amazon EKS, the implementation requires the Open Telemetry add-on. Then we have Amazon CloudWatch Observability Operator. the Amazon CloudWatch observability operator collects metrics, logs, and trace data. It sends them to Amazon CloudWatch and AWS X-Ray. Then we have Prometheus. CloudWatch. CloudWatch logs ingestion, archive storage, and data scanning rates. Apply to enable control plane logs. This is enabled for control plane logs. All these feature logs, ingestion, archive storage, and data scanning rates. And that's all. Thanks for watching.